Today's automobile engine is taken very much for granted. We know it converts gasoline into power, and power takes us where we want to go. What more could you ask? And yet, an engine such as this once was a dream going back nearly 300 years. The dream was practical, but the fuels were not. It was only when gasoline came along that a practical internal combustion engine could be built. This gleaming piece of machinery looks and is complex, yet in reality, it works on simple principles, the basic one being the four-stroke cycle. The principle may be compared to the loading and firing of an old-fashioned muzzle-loading cannon. Loading the cannon, for example, was a slow-motion counterpart of the engine cylinder's intake stroke. Ramming or packing the powder charge served the same purpose as the cylinder's compression stroke. When the cannon was fired, the expanding gases forced the shot out of the barrel, just as the piston is forced to move on the engine's power stroke. And then cleaning the barrel of burned gases was like the exhaust stroke in the engine. The analogy can be carried further by changing the cannon barrel into an accurately machined cylinder. The ramrod becomes a piston that slides up and down in the cylinder. To make the piston fit the cylinder accurately enough to form a seal, rings are set in grooves around the piston. Then, to convert the up and down motion of the piston into rotary motion, the ramrod handle becomes a connecting rod that is joined to a crankshaft. The heavy weight of a flywheel keeps the engine running smoothly between power strokes. The fuel that powers the engine is a mixture of gasoline and air fed to the cylinder by a carburetor. The carburetor works something like a lady's atomizer. In an atomizer, the air, pushed through the tube by squeezing the bulb, forces a mixture of air and perfume from the nozzle in a fine spray. In the carburetor, suction caused by the moving pistons of the engine pulls air past an open tube. This causes liquid fuel to be drawn into the airstream in the form of a fine spray. It is this combustible mixture that powers the internal combustion engine. More than 10,000 gallons of air are needed to burn each single gallon of gasoline. The pipe that carries this mixture from the carburetor to the cylinder is the intake manifold. An intake valve admits the combustible mixture into the cylinder. A spark plug produces the spark that ignites the mixture, and an exhaust valve lets out the burnt gases, which are carried away through the exhaust manifold. To make the valves open and close at the proper time requires an assembly of parts actuated by the crankshaft. Each valve should open once for every 2 revolutions of the engine. So the 2 camshafts are geared to turn at half the speed of the crankshaft. The cams are really knobs that, in turning, push up on the valve lifter and push rod and then let them down again. The top of the push rod lifts one end of the rocker arm, the other end goes down and pushes the intake valve open against the pressure of the coil spring. This admits the fuel-air mixture into the cylinder. As the intake valve closes, the piston moves up on its compression stroke. The spark plug should now fire the mixture. Let's see where we get the electricity to create the spark. The 6 or 12-volt battery current is adequate for the starter, lights, and other accessories, but it's not strong enough to fire the spark plug. So the battery current is passed through an ignition coil. Here's how the coil works. Surrounding an iron core is a primary winding and a secondary winding. When current flows in the primary winding, a magnetic field builds up. When the current flow is broken, the magnetic field collapses and produces a momentary surge of voltage as high as 20,000 volts in the secondary winding. To get this effect, a pair of contacts called breaker points continually break and reconnect the primary circuit. At the spark plug, the high voltage current arrives at just the right moment to create a clean, hot spark that ignites the air-gasoline mixture in the cylinder. With these basic parts, the engine operates in a cycle of 4 strokes of the piston. The first stroke pulls the gasoline-air mixture from the carburetor in through the open intake valve to fill the chamber in the cylinder. The second stroke compresses the mixture to about 2 tons of force on a 4-inch piston. The third, or power stroke, actually begins after the spark plug ignites the mixture. The intense heat of the fuel combustion expands the gases against the piston with a force of nearly 5.5 tons. The fourth stroke of the cycle forces the burnt gases out through the exhaust valve and manifold. The 4 strokes come in rapid succession: intake, compression, power, exhaust. Intake, compression, power, exhaust. At highway cruising speed, there may be over 4,000 strokes per minute in each cylinder of the engine. As the number of cylinders is increased, the flow of power becomes smoother. As the power stroke occurs in one cylinder, compression is going on in the second, intake in another, and exhaust in still another cylinder. Thus, one piston is always furnishing power to the crankshaft. With more than 4 cylinders, there is actually overlapping of power strokes. When the cylinders are in line, like this, each piston's connecting rod is attached to a different crank of the crankshaft. In a modern V8 engine, 2 rows of 4 cylinders each are set at an angle using a common crankshaft. The 4-stroke cycle is, of course, the same. Automotive engineers use terms such as bore, stroke, displacement to describe the capacity or size of an engine. Let's see what these terms mean. Bore is the measurement of the inside diameter of a cylinder. Stroke is the distance the piston travels. Displacement is the volume swept by the piston. The engine's displacement is the total for all cylinders. Now let's see what is meant by compression ratio. If the air-gasoline mixture is squeezed by the piston to 1/8 its volume before firing, the compression ratio is 8:1. The higher the compression ratio, that is, the more the mixture is squeezed, the more efficient and powerful the engine becomes. Here's the reason. At a low compression ratio, say 4:1, the mixture's pressure at the top of the stroke may be 100 pounds per square inch. Combustion raises this 3 to 4 times, resulting in 300 to 400 pounds per square inch push on the piston. At the higher ratio, 8:1, the mixture's pressure at the top of the stroke is 200 pounds per square inch. Again, combustion multiplies it by 3 to 4, resulting in 600 to 800 pounds per square inch push on the piston, which means more power. But there's one drawback. At a low compression ratio, when the spark ignites the fuel mixture, the flame spreads evenly across the chamber, giving a smooth power impulse. But at a high compression ratio, as the flame spreads, the unburned mixture sometimes gets so hot it ignites itself, causing a loud knock. One solution to knocking, which causes loss of power and can damage the engine, lies in the gasoline. Specialized refining, or the addition of tetraethyl lead, gives gasoline its anti-knock property. And so, it is high-octane gasoline and improved engine design that makes possible today's higher compression ratios. The internal combustion engine is basically a heat engine. It is heat produced by the combustion that expands the gases that drive the piston. 4,000 degrees Fahrenheit. Each time an explosion occurs in the cylinder, the temperature momentarily rises to as much as this figure. Nearly a third of this heat is transformed into useful power. Another third is dissipated with the exhaust gases. The remaining heat goes into the engine parts. Most of this heat must be removed by the cooling system to avoid damage to the engine. A water jacket surrounding parts of the cylinders, the valves, and the spark plugs contains circulating water that carries off most of the heat. This side view of the engine shows the cooling system in diagram. A pump forces water from the bottom of the radiator through the water jacket, where it absorbs heat from the engine parts, and then back to the radiator for cooling. The fan pulls air through the radiator to carry heat away from the hot water. A thermostat in the system regulates the cooling. When the engine is cold, the thermostat controls the flow of water to the radiator so that the engine will warm up quickly. When the water gets hot, between 160 to 180 degrees, the thermostat opens and lets the water flow to the radiator for cooling. Today's engine, in theory, is not too far removed from the visions of yesterday's dreamers. But in design and manufacture, there the true genius of our century's engineers is evident. For each part, made, remember, by the identical thousands, is a precision piece. Each part fits with other precision pieces, and miraculously, the whole comes together as a smoothly working power plant. The crankshaft is the first item. It goes under the engine block, and so we'll have to turn the block bottom up. These are the main bearing inserts. Now we're ready for the crankshaft. Bearing caps for the crankshaft. Now the pistons. Every connecting rod gets its bearing insert. This is the camshaft. It will be tied in with the crankshaft by a chain drive and harmonic balancer. The oil pump is put together. Next, the oil pan. The oil filter assembly. Now, the flywheel. The two cylinder heads and the intake and exhaust valves get together. And then the 16 valve springs. Now the valve lifters and push rods, 16 of each kind. Then the rocker arms. The breather fixture and the intake manifold go on next. Then the two exhaust manifolds. This is the fuel pump, and here comes the carburetor. These are the fuel lines which connect fuel pump and carburetor. Next, the ignition coil, the distributor drive mechanism, and the ignition harness. These are shields to protect the spark plug leads. Now the valve covers go on, and the air cleaner. Time now for the starter to go in place. This is the water pump. The generator. The fan belt. This then is the power plant that runs our cars. It may develop 200 or 300 or more horsepower. But all that power is useless unless it is transmitted to the wheels. A train of devices does this. First in the train is the clutch with its diaphragm spring and its friction disc, which connects and disconnects the engine and the transmission without stopping the car or the engine. The transmission is a mechanism of gears that makes it possible to vary the speed of the engine and the wheels to take care of differences in load and speed of the car. Large and small gears join in various combinations to give us the well-known low, second, and high. How the transmission works can be shown with this diagram. To start the car moving, a shift into low gear gives high turning effort and low speed at the rear wheels. Once the car is in motion, such great turning effort is no longer needed, and a shift to second gives a somewhat higher speed at the rear wheels. Next, a shift into high connects the engine and the wheels directly. Now the engine power is used most effectively for normal driving. In reverse, as in low gear, great turning effort at low speed is needed. Now, of course, the drive shaft turns in the opposite direction. A large proportion of modern cars are built with an automatic transmission. The clutch pedal and the gear shift lever are eliminated, and the transmission automatically adjusts the relationship between engine speed and car speed for the best performance. A universal joint between the transmission and the drive shaft allows the rear axle to move up and down. The rear axle is made up of two sets of gears. The drive gears transmit power from the drive shaft to the rear axle. The differential gears allow independent rotation of each wheel, which is necessary in going around corners. The chassis is now fitted with the entire power-producing mechanism and the means of transmitting that power to the rear wheels. The car will run, but it also has to stop. The brake is composed of shoes faced with friction material and a drum of hard metal. When the brake pedal is pushed, the brake shoe pushes against the rotating drum and stops the turning wheel. Smooth, equalized braking is gained through the hydraulic braking system. And in many modern cars, power brakes can stop the car with only the slightest pressure on the pedal. The steering mechanism is strong, dependable, and easy to operate. When the steering wheel is turned, the steering gear causes an arm to move and change the direction of the front wheels. Power steering in many cars makes the effort needed at the steering wheel almost negligible. Thus we have the modern automobile that is the envy of the world. In it are built performance, efficiency, economy, and safety. Any one of many body styles will give it comfort and smart appearance. The modern car has everything, in fact, except the skill of the driver. And in this electronic age, the restless minds of the automotive engineers may someday build even that into this marvelous machine.